In this problem, we're going to take a rod, let the rod pivot and swing and hit a ball. Once it hits the ball, the rod is going to stop swinging and the ball is going to move forward. So a system consists of a ball of mass m2, that's the mass of the ball, and a uniform rod of mass m1 and length d. The rod is attached to a horizontal frictionless table, nice, by a pivot point P and initially rotates at an angular speed omega as shown above in that picture. The rotational inertia, which remember the symbol for that is an I, is 1/3 m1d squared. So the rod strikes the ball, which is initially at rest, which means there is no momentum for the ball to begin with. And as a result of the collision, the rod is stopped, so there's no momentum for the rod afterward. And the ball moves in the direction shown above, which is to the right. Express all your answers in terms of m1, m2, d, and any fundamental constants that we have. So first off, part A, derive an expression for the angular momentum of the rod at point P before the collision. If you remember, the symbol for angular momentum is an uppercase L, and it has two parts to it. There's an angular component that is I omega, but it also has a linear component that is RMV. So if we're looking for the angular momentum of the rod is spinning or rotating or moving angularly, which means we're going to look at the angular part, not the linear part. Well, above they give us the I equation. That was very nice of them. So 1/3 m1d squared. And then we tack on our omega because it says we could keep omega in our answer. And that is the answer to part A. Super easy. Part B. Derive an expression for the speed v of the ball after the collision. Well, if we're dealing with collisions, remember that we have to be dealing with momentum. Because one of the objects is rotating, it means we have to be dealing with angular momentum. So we can say the angular momentum in has to equal the angular momentum out. We just found the angular momentum in, 1/3 m1d squared omega. And the angular momentum out is caused because the ball is moving forward in a straight line. That means that we're not going to look at the angular part of that, we'll look at the linear part. So generically speaking, we'll say this is RMV. Now let's look at that specifically. How far away is the ball from the pivot point? It is also a distance of d, so my radius will be d. The mass of the ball, it tells us, is m2, and we're looking for the velocity of the ball. So 1/3 m1 d squared omega. That means that I can cancel out a d, and divide by m2. So my velocity will be 1/3 m1 over m2 d omega. And that's our answer to part B. Now, part C. Assuming that this collision is elastic, remembering that elastic collisions deal with conservation of energy, so I'm going to have a kinetic energy in has to equal my kinetic energy out. So what kind of kinetic energy do we have to begin with? We had the rod rotating, so it's got to be rotational kinetic energy, 1/2 I omega squared. And what kind of kinetic energy did we have coming out? Well, if the rod stopped and the ball is moving forward in a straight line, it's got to be linear kinetic energy, 1/2 mv squared. Plug and chug now. So I can get rid of my halves. My I value is 1/3 m1d squared. I can keep this omega there, omega squared. This mass is m2. And then the velocity, we already found the velocity of it down here, so I'm going to square this down here. It's going to be 1/9 m1 squared over m2 squared d squared omega squared, and then plug that in up here. So 1/9 m1 squared over m2 squared d squared omega squared. And then I can simplify. D squared omega squared will cancel out with d squared omega squared. One of the m2's will cancel out with one of the m2's. One of the m1's will cancel out with one of the m1's. And then a third, I can get rid of that on this side by taking a 3 out of that and saying 1/3. So I have 1 equals 1/3 m1 over m2, which is really close to the ratio that we have there. So I'm going to move the 3 to the other side and say 3:1 is equal to m1 to m2. And that's your answer to part C. Last one. In part D, a new ball with the same mass m1, so now we don't have to deal with this m1, m2, we can keep it all as just m1, is placed at distance x, so some distance away from the pivot point. Again, assuming that the collision is elastic, that means that I'm going to be dealing with some kind of kinetic energy in kinetic energy out. For what value x will the rod stop moving after hitting the ball, which means I'm going to also again be dealing with angular momentum because that's a collision. Angular momentum in, angular momentum out. So let's start with that one. The angular momentum in, again, is the rotating of that, so it's got to be I omega. We can say that that I omega is going to be 1/3 md squared omega, because they gave us the I value up here, and then we just tack on our omega to that. Then we can say that our angular momentum out is going to be RMV, because it's the momentum of the ball. So the distance, the radius, is going to be that x value, x. The mass was m, and then there is our velocity. So I can simplify by dividing m, and that's about as far as I can go. I can solve this for velocity and say 1/3 d squared omega over x is going to be the velocity of the ball. Now, where can I go with that? Velocity has to deal with kinetic energy, so over here I'm going to say the kinetic energy in was the kinetic energy of the rod rotating, 1/2 I omega squared again. And the kinetic energy out will be the motion of the ball in a straight line, which would be 1/2 mv squared. My halves will cancel out. The I value was given to us, so 1/3 md squared omega squared. My mass of the ball is also m, and the velocity we just found over here, so I can square this also, 1/9 d to the 4th omega squared over x squared, and put that in up here. So 1/3 md squared omega squared equals m 1/9 d to the 4th omega squared over x squared. And now we can do some more math magic. Get rid of our m, get rid of our m, get rid of the 3, make this be 1/3. The omega squareds will cancel out. Our d squared can cancel out with 2 of those, and again I'm left with 1 on that side, and a d squared over 3x squared. What are we looking for? We're looking for what value of x, which means I want to solve for x. So 3x squared equals d squared. And then I can say x squared equals, I guess I could have kept the 3 down there, 1/3 d squared, which means if I square root that, I'm going to have x is equal to the square root, is equal to d over the square root of 3. And that's going to be our value for x in that problem.